Well. Interestingly, as I was telling you, last time we were looking at the enthalpy of formation of compounds, and we're like enthalpy of formation refers to the heat change when 1 mole of a compound is formed from its constituent elements in their normal state, so in their normal physical states. And the moment we add the word standard and it becomes standard enthalpy of formation, we say that that is the heat change that occurs when 1 mole of the compound or when 1 mole of the substance is formed from its constituent elements at standard temperature and pressure, or at 298 kelvins and 760 millimeters of mercury, or 1 atmosphere. So today we are going to look at okay, we are continuing from where we stopped, and since we had looked at enthalpy of combustion, and we looked at the experiment for enthalpy of combustion, it is from that note that we are going to see how best we can calculate, how best we can concentrate on the calculations, and we see whether we can get them out very well. I'm sharing my screen, and today's work includes something that needs much attention from you. So we really needed to be extra attentive, yeah? Well, okay, questions are here. Okay, we are going to begin right away with the calculations. And there we are. So we are going to write calculations. I told you after Hess's law, that is when we shall go to the Born-Haber cycles. But today we are going to discuss those calculations that involve heats of combustion, calculations that involve enthalpy combustion. Okay. So basically here, I'm going to give you questions and we start calculating. Number one, if the heat of formation guys, a moment. If the heat of formation of carbon dioxide is -393 kilojoules per mole, heat of formation of water is -286 kilojoules per mole, and heat of combustion of butane is negative 2,877 kilojoules per mole. Calculate the standard heat of formation, of butane. I will not give you any equation because equations will not be given to you. So in most of the cases, you have to be smart and say, I want to first teach you the other induction method of cancelling the equations. And then after, that is when we shall go to Hess's law and Laplace's, then we see how we can use the Born-Haber cycle to calculate. Well, here, the first thing is to know what have you been given. They have given us the heat of formation, enthalpy of formation. Even here, they have given us enthalpy of formation. Here, they have given us heat of combustion. Now, you can generate these equations on your own if you really know the meaning of these terms. If the question is saying calculate the standard heat of formation of butane, it means that you need to first know what is butane. How do I write butane? That one will give us the required equation. Heat of formation of butane. Butane is a hydrocarbon, and hydrocarbons consist of carbon and hydrogen atoms only. So if they want the standard heat of formation of butane, it means that I am forming butane. Meaning, butane, you must be knowing, first of all, what is butane. Butane is a C4H10, but heat of formation refers to the heat change or energy change that occurs when 1 mole of a substance is formed from its constituent elements, and we are forming 1 mole. So at the products, you shouldn't put any balancing figure. So this is C4H10, meaning the elements are carbon and hydrogen. So we shall have equation required. Equation for the reaction that is required. Equation for the reaction required. Equation for the reaction required is, we are having carbon. Carbon is a solid because we want enthalpy formation, meaning carbon must be, this butane must be formed from its constituent elements. So carbon plus another one is hydrogen. Hydrogen is a gas. This will give us butane. Butane is C4H10. But you shouldn't ever be tempted to balance here at butane. Don't balance at butane. Just because we say that enthalpy formation, 1 mole of your compound is formed. So never be tempted to put any figure here. Instead, balance the rest. Carbons are 4, put here a carbon, put here a 4, and hydrogens are 10, but here I have 2, so put here 5. After balancing this equation, we shall be needing the enthalpy of formation, HF theta, which is equal to what I don't know. I'm forming butane. I request everyone who has entered class to mute. Enthalpy of formation of butane is what we shall need. Then equations for the reactions given. We have been given some other reactions, and those are the reactions that I need to ponder over right now. Equations for reactions. The first reaction has been given as, heat of formation of carbon dioxide. I'm forming carbon dioxide, meaning if they say heat of formation, I'm forming 1 mole of carbon dioxide from carbon and oxygen. So the first equation would be carbon, which is a solid, plus oxygen, which is a gas, and I'm strictly forming 1 mole. I'm forming 1 mole of carbon dioxide because of the word heat of formation, and this is gas. Let me call this one might be H1. Another one, they are giving heat of formation of water. Water is H2O. If they say heat of formation of water, it means I'm forming 1 mole of water from constituent elements, which are hydrogen and oxygen. So I'm going to have hydrogen gas plus oxygen gas, and this is going to give me 1 mole of water. So I'll write H2O, 1 mole of water, so liquid, and this one will be DH2. So since I'm forming 1 mole of water, where do I need to balance? Oxygen here I have 1, but here I have 2, so I have to put a half here. You shouldn't be tempted to balance here unless it is another heat. But if it is heat of formation, never balance on the product side. Okay, then another one they have given me, heat of combustion of butane. Heat of combustion of butane. So butane is C4H10. It's a gas. If they say heat of combustion, it means that it is oxygen gas that supports burning or combustion. But hydrocarbons burn in oxygen, even if provided something has CH, they're going to burn is in oxygen, you're going to form carbon dioxide and water. So you'll have carbon dioxide gas and water. Some of the things you must get them as fast as possible. Heat of combustion, and this is liquid. But remember, heat of combustion is negative. We say that when a substance burns in air, there is heat that is emitted. So heat of combustion is negative. So let me say that this is negative DH3. Interesting. But this equation is not balanced. And here you are allowed to balance even this side of the products because it is heat of combustion, not heat of formation. So if I'm to balance the product side, carbon is 4. Yeah, carbon is 4, but this side I have 1. So allow me put here a 4. Hydrogens are 10. Hydrogens are 10, but here I have only 2 hydrogens. So allow me put here a 5. Oxygens are 2. Oxygens are 2. Here I have 2 oxygens. Yeah, but this side I have 8, 13. So to make them 13 also here, I'll put 13, but because I want these 2 to cancel out, I will say over 2. If you are with me on these 3 equations before I go to multiplying and doing whatnot, please type a yes if you're free with the steps I've written here. Please type yes. Guys, I need those yeses. Don't be jealous. Don't be jealous. Let me see people are not sending me yes. If it's not a yes, you have to ask. Wow, I'm enjoying. Now, the steps where I'm going are the most logical steps. Generating this equation is easy. It is all about knowing the reactions that take place. Let's treat this. Let's treat these equations. Let's treat these equations. How am I going to treat these equations? If you want to work it out very successfully, you should always use this required equation. Gumperom, leave my screen alone, please. You should always look at this equation required for the reaction that is required, and you compare it with these other individual equations. For example, in the required equation, we have 4 carbons, but in the equation for the reaction, we have 1 carbon. Implying that to get 4 carbons of the required equation, we shall multiply equation 1 by 4. That is what you should know. you check on the equation required, you compare it with the equation for the reactions that you want. Since I have 4 carbons, it means that this carbon equation 1, to make them 4 carbons, we have to multiply it by 4. So if you multiply equation 1 by 4, we shall, let me call this one equation 1, let me call this one equation 2, let me call this one equation 3. Ladies and gentlemen, listening to me, if you want a 4 carbon, you need to multiply a 4 throughout equation 1. So let me note it for you here. And I say multiply 4 throughout equation 1. Multiply a 4 throughout equation 1. What does it mean? We shall have 4 carbons. We shall have 4 carbons. We shall have 4 carbons solid. Plus 4 oxygens. We just multiply and we shall form 4 carbon dioxide. 4 carbon dioxide gas molecules, and this heat change is going to be 4DH1, meaning we shall multiply the enthalpy of combustion by 4. If you're with me on that step, please type yes. If you're with me on that step, please type yes. If you're with me on that step, please type yes. If you're with me on that step, please type yes. I see people yesing me. Okay, if that's the case, then check equation, check hydrogen. We have 5 moles of hydrogen, and here we have 1. So we shall multiply equation 2 by 5. Multiply equation 2 by 5. So we shall have 5 hydrogen molecules gas plus 5/2, because when you multiply 5.5, we shall have 5/2 oxygen molecules, and we shall form 5 molecules of water. If you form 5 molecules of water, this equation will be 5DH2. 5DH2. Then equation 4, rather equation 3. When you check this side, we have the product on the right-hand side. The product is on the right-hand side. Butane is on the right-hand side, but this side, butane is on the left-hand side. Yeah, and we have 1 mole, meaning we don't have to change anything in this equation. You have 1 mole here, you have 1 mole here. But surprisingly, this one is on the right-hand side here, and here it is in the left-hand side. So what do we do for that case? We just interchange the equation. We shall just interchange these products. We bring them this side of reactants, and we bring the reactants to the products, so that what is on the right-hand side in the required equation should be on the right-hand side when we are generating these equations. So we shall interchange equation 3. We shall interchange equation 3, meaning we shall have 4 carbon dioxide molecules plus 5 water molecules. I've brought the reactants first, and this will give me butane C4H10 this side gas, and then 13/2 oxygen molecules. And interchanging this doesn't change the other. It will keep negative DH3. It will keep negative DH3 because this was as a result of combustion. It was as a result of combustion. If you're with me on how I've generated these equations, if you've generated equations together with me, don't be jealous, simply type a yes. If you're with me on generating these equations, don't be jealous, just type yes. Type yes if you're with me on generating the equations, then I show you the next logic ahead. Nganda Davis, yes. Tumushime Nicholas, yes. Where are others? Onenichan, where are you? Mariam, Maria, Vanessa, Vivian, you understanding. I love this. I said you just say yes, you type, but you don't talk. Otherwise, when you talk, it becomes very stubborn for me to control this. Now, the step that follows here is to cross. We are going to cancel, and we see if we cancel, whether we be left with the equation required. That is what I'm going to do. If I cancel, am I left with the equation required? Yes. Let's see. We don't need to cancel carbon because we shall need it in the equation required. We don't need to cancel hydrogen, I will need it. We don't cancel butane, I will need it. So I will cancel the rest. 4 carbon dioxide, 4 carbon dioxide. 5 molecules of water, 5 molecules of water. Oxygen 13/2. The moment you add these two, they should give you 13/2. You see, 4 plus 5/2, LCM is 2. When you multiply it here, it will be 8 plus 5, which will be 13/2. So 13/2 will cancel with 5/2 and 4, implying that I'll be left with the 4 carbons plus 5 hydrogens to give me butane, which is the required equation. So this one, we shall obtain the required equation, thus obtaining the required equation. So after getting the required equation, we shall see how to get the enthalpy of formation. HF theta of formation of butane C4H10 is going to be equaling to 4DH1 plus 5DH2, 5DH2, then minus DH3. We subtract DH3 because it's automatically negative. And what we shall get is 4 times DH1. DH1 was enthalpy of formation of carbon dioxide, which is negative 393. Negative 393. I will add 5 times DH2, enthalpy of formation of water, which is negative 286. Then minus DH3, which is the enthalpy of combustion of butane, which is also a negative 2877. The moment you work on this, ladies and gentlemen of God, you are going to get the value equivalent to, you're going to get the value equivalent to, because these two will make a 3002, negative 3002, and then this one will make a plus. Okay, let me write the overall answer without wasting your time. The overall answer will be negative 2,716 kilojoules per mole. Kilojoules per mole. Kilojoules per mole. Kilojoules per mole. Excellent. Okay, you compute well. I may not be perfect in computation, but the most important thing is giving you the steps. If you've understood how we calculate this thing before you go to the Born-Haber cycles, type yes. I'm going to add you more examples. I'm going to add you more examples, and then we see how we can go about them. If you're with me, type yes, and I take it to example number 2. I feel like taking it to example number 2, but that is up if at all you first confirm that you are with me. Interesting. But members, you have not connected in your colleagues, because I see the people I had next week are the same people, rather than people I had last week are the same people I'm still having. You do great by bringing in your fellows. Please, 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 please. Okay, so without wasting time, let me take you to example number 2. Let me take you to example number 2 without wasting any time of yours. Example 2. I told you this week we must move far. We must move far. Example 2. Study the table below. Study the table below. And answer questions. Study the table below and answer questions or question. So we are having substance. We are having substance. we are having a substance, and here we are having enthalpy of combustion. So they gave us enthalpies of combustion, enthalpy of combustion, and enthalpy of combustion in this case, this is in kilojoules per mole. We're having carbon, we're having sulfur, we're having carbon disulfide. So guys, this is my table, and I want to see how we can use the table to calculate. So the question is calculate the enthalpy of formation of carbon disulfide. Capture the enthalpy of formation of carbon disulfide. Yeah, you correct the calculation we've done previously and write the correct answer. Hope you have calculators. So members, they want us to calculate the enthalpy of formation of carbon disulfide. When we say carbon disulfide, I've not given any equation. We have to generate this equation by ourselves. So equation required. Enthalpy of formation of carbon disulfide. Carbon disulfide is carbon and a sulfide, disulfide, CS2, and this is a liquid. So enthalpy of formation, we are forming 1 mole of carbon disulfide from its constituent elements, which is carbon and sulfur. So equation required for the reaction required, equation for the reaction required is going to be carbon, which is a solid, plus sulfur, which is a solid, and we shall give carbon disulfide, which is a liquid. And they want enthalpy of formation of that carbon disulfide, which I don't know. Balancing carbon 1, sulfur 2, rather sulfur 1, sulfur 2, so I'm putting it 2. The moment is enthalpy of formation, you really don't need to balance on this sulfur. From here, we shall write the equations for the reactions required. Equations for reactions. The reactions we have, enthalpy of combustion of carbon. So carbon undergoes combustion, that is in oxygen gas, to form carbon dioxide. And I will call this one the H1. And that the H1 actually has been given as negative 393.3 kilojoules per mole. The equation is self-balanced. Enthalpy of combustion of sulfur. Sulfur undergoes combustion in oxygen gas to form sulfur dioxide gas. And this is going to give me the H2, which is negative 293.72 kilojoules per mole. And then we have enthalpy of combustion of carbon disulfide. Carbon disulfide will undergo, it is a liquid, it will undergo combustion in oxygen to form oxides of constituent elements. So we shall form carbon dioxide and sulfur dioxide. Carbon dioxide gas and sulfur dioxide gas. Sulfur is 2. Since it is combustion, you can balance even the product. Sulfur is 2, sulfur is 1. Put here a 2. Oxygens are 4 plus 2, 6. Put here a 3. And this is the H3. which has been given as negative 1108.76 kilojoules per mole. After treatment of this equation, then we have to go ahead and compare with the equation required, and then we see if it gives us the equation. So we have to check. Carbon, we have one. Carbon, we have one. In the equation required, we have one, and the equation for the reaction also have one. So we don't need to cancel. So the first equation will keep the first equation the way it is. So we shall have carbon solid plus oxygen gas. It will give us carbon dioxide gas. Allow me call this one positive H1. This week, thermochemistry, if it may be done even, because there is no big deal, provided you understand the things very well, we shall move very, very, very successfully. Then another one, we have sulfur. So sulfur, we have 2, but this side we have 1. So we shall multiply equation 2 by 1. So if you multiply equation 2 by 1, we shall have, multiply equation 2 by 1, we shall have 2 sulfur. No, if you multiply equation 2 by 2, we shall have 2 sulfur plus 2 oxygen molecules, giving us 2 sulfur dioxide molecules of a gas. So this is the H2. Equation 3, we have carbon disulfide 1 mole, carbon disulfide 1 mole. Surprisingly, on the right-hand side, on the left-hand side, interchange the equations. If you interchange equation 3, we shall have carbon dioxide gas plus 2 sulfur dioxide gas molecules to give you carbon disulfide liquid and 3 molecules of oxygen gas, which gives us the enthalpy. Since this one we shall call it negative DH3. Oh my God! Interestingly, we can now. This was 2DH2. This one kept DH1. So what do we do? Let's see if they balance. Carbon. I don't need to cancel carbon. Moreover, it is nowhere else. And even in the required equation, I need it. I do not need to cancel sulfur because in the equation I need it. But even carbon disulfide, I don't need to cancel it because I need it in the equation. But carbon dioxide can go. Yeah, 2 sulfur dioxide molecules can go. I don't want oxygen at all. So 1 mole of oxygen plus 2 moles of oxygen, they become 3 moles, which cancel with these moles. As sulfur dioxide, I didn't cancel it. It was supposed to be cancelled. So I'll be remaining with the carbon plus 2 sulfur to give us carbon disulfide, which is the same carbon plus 2 sulfur to give us carbon disulfide. So that's obtaining the required equation. Even if you don't write this note, that's obtaining the required equation. So after doing this, after obtaining the required equation, what do we do? What do we do? What I do here, I have to generate the calculation procedure. So the enthalpy of formation of carbon disulfide is going to be DH1 plus 2DH2 minus DH3. So DH1 is negative 393.3 plus 2DH2, which will be plus 2 into DH2, which is negative 293.72 minus DH3, which is negative 1108.76. And this one will overall give you the answer. Compute, the answer will be positive 128.02 kilojoules per mole. That is what we shall have. If you're with me, guys, type yes. If you are with me, guys, type a yes, because I have more 2 examples to do for you. I give you exercises. We introduce Born-Haber cycle. Okay, from this point, example number 3, I'm sending this work to your WhatsApp so that we minimize copying time here. And number 3, is given that enthalpy of combustion of ethanol is negative 1371 kilojoules per mole. I'm sorry for that network breakdown. But the question was, given that enthalpy of combustion, enthalpy of combustion of ethanol is negative 1371 kilojoules per mole. Enthalpy of formation of carbon dioxide is negative 393. Guys, my network has gotten issues, but I don't know. You've said enthalpy of combustion of ethanol, enthalpy of, guys, I have visitors, you have to. Enthalpy of combustion of ethanol has been given as negative 371. Enthalpy of formation of ethanol, negative 1371 kilojoules per mole. Then enthalpy of formation of carbon dioxide is negative 393 kilojoules per mole. Then enthalpy of formation of water is negative 286 kilojoules per mole. Calculate the heat of formation of ethanol. Calculate the heat of formation of ethanol. Calculate the heat of formation of ethanol. How do we go about this? Heat of formation of ethanol. You need first equation for the reaction required. Formation of ethanol. Which equation are we going to write? Which elements are you going to use? Because ethanol is CH2 or CH3, CH2 OH, or one can write it as C2 H5 OH. Meaning that for this particular case, you have carbon, hydrogen, and oxygen. So your equation for the equation of the required reaction is going to be carbon, because the moment they say formation, it must come from constituent elements. Carbon plus hydrogen gas plus oxygen gas to give me ethanol, CH3, CH2, OH. And take it as a liquid. Now, carbon, you have one. Here, carbons, there are two. So here we shall have two carbons. Hydrogens are two, but here hydrogens are 3, 5, 6. So if hydrogens are 6, it means that here you have to put a 3. Hydrogens are 2, hydrogen is 1. So we shall put a half. We shall balance this one by putting a half. So that is the equation of enthalpy of formation of ethanol. And we don't know that enthalpy of formation of ethanol. HF theta, we don't know. Step 2, now other equations for the reactions. Reactions involved. Reactions involved, we have enthalpy of combustion of ethanol. Ethanol is undergoing combustion. So the reaction number 1 is ethanol, CH3, CH2, OH, liquid, is undergoing combustion in oxygen gas to form, the moment I said you have carbon and hydrogen, carbon dioxide and water. Do we need to balance? I guess yes. Carbon 2, carbon 1. Bring that one, place it there. Hydrogens 5, 6, but here we have 2. So bring a 3 and put it here. Oxygens, they are 6 plus this 8. Yeah. 8 or 7. These ones are 4 plus this 7. But this is already 1, so we miss 6. So I put here 3. And this is the H1. The H1 was given as negative 1371 kilojoules per mole. Reaction 2, enthalpy formation of carbon dioxide. We are forming carbon dioxide. So carbon, solid, is reacting with oxygen, the constituent elements, to give us the carbon dioxide gas. And this is BH2. This will give us BH2, which is negative 393 kilojoules per mole. Then, oh, it is formation. Sorry. It is not combustion. It is formation. But I'm talking about formation of carbon dioxide. Yeah. Carbon dioxide is carbon and oxygen. Then the third one, formation of water. we shall say hydrogen plus oxygen. These two will give us water. But on balancing this, on oxygen, we shall put a half. We don't balance using this side when it is enthalpy of formation of the products. A moment a bit. Okay, so from here, what next? What next? We are going to see how these equations are balanced, or how we cancel them to generate the other required equation. So what do we do? This is DH3. Which is equal to negative 286. Kilojoules per mole. After obtaining these three equations, let's see how we treat them. The first equation, compare what you have and what you were given. This one is having ethanol, and this one is also having ethanol. One more, but right-hand side, left-hand side. So we shall begin by interchanging. So we shall have 2 carbon dioxide gas molecules plus 2 carbon dioxide molecules plus 3 molecules of water. After interchanging this equation, it will give us ethanol, CH3, so we shall form ethanol plus 3 oxygen gas molecules, right? So now I've interchanged this equation. The moment I interchange, meaning this one will be negative DH1. Then required equation has 2 carbon atoms, but in the reaction equation we have 1 carbon, meaning we shall multiply equation 2 by 2. When you multiply equation 2 by 2, we shall have 2 carbons plus 2 oxygens, giving us 2 carbon dioxide gas molecules. And this one will give us 2 DH2. Emily, come for what you sent for. 2 DH2. Then the third equation, here we are having 3. The third equation, because we are having hydrogen and oxygen. Oxygen is balanced, a half. Yeah, it is a half. So equation 3, we need to work on the hydrogen. Hydrogen is 3 in the required equation. Hydrogen is 1 here. So we shall multiply equation 3 by 3. Oxygen is okay, a half. Hydrogen is 3, 1. So multiply equation 3 by 3. So it will be 3 hydrogens plus, when multiply oxygens, it will be 3 out of 2. 3 out of 2 oxygen, we shall form 3 molecules of water. We have been multiplying by DH3 by 3. So if you're with me here, members, type yes, and I see you. If you're with me here, type a yes, and I see you, because we are going to cancel them now. We are going to cancel these equations, and we see. Now, what happens is, we shall cancel carbon dioxide and carbon dioxide. Shall cancel 3 molecules of water, 3 molecules of water. Yeah. What else do I need to cancel? What else do I need to cancel? Because the required equation has a half oxygen. Do I need to cancel carbon? No, I need carbon, 2 carbons. I need 3 hydrogens. So the most important thing is on oxygen. Now, oxygen, I will cancel this 3 with this 3 and I remain with a half of oxygen. Or in other words, you have 2 oxygens, you have 3 over 2 oxygens. When you add them up, 2 plus 3 out of 2, this is 7 over 2. When we subtract these 3, I want to show you how we cancel. When you subtract these 3, you'll be remaining with LCM is 2, so 7 minus 6, which is a half. Yeah. So in other words, what will happen is you are going to cancel these 3 with the 2. Then we shall be left with a half only. So we shall be left with a half oxygen. This equation is automatic. The moment you balance very well, automatically on crossing, it must come out. If you the problem comes in when you have failed to balance. But the moment you balance this equation very well, I expect you to get the answer very properly. So it would follow that enthalpy of formation of ethanol is going to be, it's going to be negative DH1, where we interchange it from negative DH1, that is what we are beginning with now, because it's no longer DH3. Negative DH1 plus 2 DH2 plus 3 DH3. Negative DH1. DH1 is this. So it's negative will be negative DH1, which is negative 1, 3, 7 plus 2 DH1, DH2 is going to be negative 393 plus 3 into DH3, which is negative 286. 286. On working about this, you're going to get the answer like negative 273 kilojoule per mole. That is my third example. I'm left with only one example. I give you exercise. If you're with me, let me know so that I see how to handle the rest. Lastly, Lastly, that is my final example. And then I torture you with exercise. Okay, you calculate well and get, because me, I'm using a phone to put. You calculate well and get the answer. Me, I'm using a phone. Finally, number 4, I guess these examples will be enough. Given that enthalpy of combustion of ethane is -1260 kilojoule per mole, comma, enthalpy of combustion of ethanol, enthalpy of combustion guys, my network, but it's stabilizing. I had said enthalpy of combustion of ethane is -1260 kilojoules per mole, and enthalpy of combustion of ethanol is -1160 kilojoule per mole. Calculate the heat change of the reaction. Calculate the heat change of the reaction. Okay, they wrote for you the equation of the reaction. Calculate the heat change of the reaction. Ethane, C2H2, that is ethane gas, is reacting with water, hydrolysis of ethane, water liquid, because we do the normal physical states to form ethanol, CH3, CHO. In organic chemistry, we shall interpret ethanol as an aldehyde when we reach there. So they want us to calculate the enthalpy for that reaction. What do you consider? Equation required has been written for you already, because they say calculate the heat change for the reaction. So equation for the reaction is ethane plus water to give us ethanol. That is enthalpy. Then from there, they gave us enthalpies of combustion. They gave us combustion of ethane. So ethane will undergo combustion. In oxygen to form carbon dioxide, provided you see carbon and oxygen, carbon and hydrogen undergoing combustion. You form carbon dioxide gas and water. Is the equation balanced? No. Carbon 2, carbon 1, put here 2. Oxygen is 2, but these ones are 4, 5. So we shall put 5 and we divide by 2 to eliminate these 2. What else? Yeah, it is like that. So this will give us the H1, which is -1260 kilojoule per mole. Then after this, So from here, we shall have also enthalpy of combustion of ethanol. They've already given you the formula. Whenever they see that the equation will give you challenge, they will always write for you something there. So ethanol, we shall have the equation CH3, CHO, liquid, plus oxygen. Provided you see carbon and hydrogen inside there, it must give us carbon dioxide and water. This is DH2, which is -1160 kilojoule per mole. Now, balancing carbon is 2, put here 2, oxygen is 4,5, this is 2. So what do I miss? Hydrogen, sorry. Hydrogens are 3, 4. So I need to first put here 2. Oxygen becomes 4, 6. These are 2, 3. So I will put 5/2. So that this one goes with this, 5 plus 1 becomes 6. So after doing this, I start comparing them with the equation I want. 1 ethane, 1 ethane. We shall leave that equation the way it is. So it will keep C2H2 gas plus 5/2 oxygen gas to give us 2 carbon dioxide gas and the water liquid. This one will give us, we shall take it as DH1. 2, ethanol is in the product 1 mole, but here it is in the reactant 1 mole. So we shall interchange that equation and we shall have 2 carbon dioxide gas molecules plus 2 water gas liquid molecules, forming ethanol CH3CHO liquid plus 5/2 oxygen gas. And I call this one negative DH2 because of the interchange. Cancelling 5/2 oxygen, 5/2 oxygen. Yeah. 2 water, here I have 1 water. So these 2 will go with these 2 here. These 2 here will reduce this water because I have 2 water molecules, here I have 1 water molecule. So I will just cancel. Yeah, I'll just cancel. Then carbon dioxide, do I need carbon dioxide? No. 2 carbon dioxide go away, 2 carbon dioxide go away. So ethane plus water will give us ethanol. So I have obtained the required equation. So enthalpy for the reaction, enthalpy for the reaction would be equaling to DH1 minus DH2. So this is going to be -1260 minus -1160. This will give you the answer in kilojoule per mole. If you believe that if I give you exercise now, you can chop it, type yes. If you say, if you give me exercise now, I will do it. Type yes. If you know, if you give an exercise you can handle, type yes. And I don't delay. Yeah, I don't delay. Let me give you exercise already. I do not delay. People can handle. So if you can handle, let me give you that exercise. Those numbers, please endeavor to do them. So from there, we shall go to laws. We shall go to laws. without wasting time because I have 5 minutes. So let me introduce the laws. Let me introduce the laws. There we shall have gone. So after having looked at all that we've looked at, we shall write and we say laws of thermochemistry. Laws of thermochemistry. Laws of thermochemistry. And the first law we are going to talk about law number 1. Of course, we have Lavoisier-Laplace and Hess's law. But let's begin with Hess's law. This is the one that will take us to the Born-Haber cycle. Hess's law of constant heat summation. Hess's law of constant heat summation. Now, this is where we shall be drawing the Born-Haber cycle to calculate. Now, let me assume that I'm just introducing it. I'm assuming that I have A. From A, you can go to B. From B, you can go to C. From C, you can go to D. But someone can be like, me, I can go direct to D. So I'm assuming this will be, one can take root. So I can call this one my root 1 from A direct to D. This is my root 1. Oh, someone can go stopping until they get to D. You know, even if you eat slowly, the source must be done. So let me call this one my second root. So this is root 2. Now, it would imply that enthalpy for root 1 must be equal to enthalpy for root 2. Enthalpy for root 1, let me call this one the H1. And let me call this one the stoppages, the H2, the H3, the H4. Implying that since enthalpy in root 1 is equal to enthalpy in root 2, then to imply that enthalpy in root 1, which is the H1, enthalpy in root 1, the H1, is equal to enthalpy in root 2, which is the H2, plus enthalpy in root 3, which is the H3, plus enthalpy in root 4, which is the H4. This is one root. But to get to this one root, you sum up. That's why we call it Hess's law of constant heat summation. It means that whether you go direct or you go stopping, you must get there. So the H1, one has jumped direct. But for the one of the root 2 has to go through the H1, the H2, the H4. But you have reached also. So this is what we call constant heat formation. Now, when we are stating this law, I'll give you 3 alternatives and you will talk about what you know. So there are very, 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 very few reactions whose enthalpy change can be measured directly by measuring the change in temperature. For those enthalpies that can be determined directly, Hess's law can be employed. For example, it is not possible to measure the enthalpy formation of ethanol in the lab because it is not possible to synthesize ethanol from carbon, hydrogen, and oxygen. You cannot get it. You cannot get enthalpy formation of ethanol from the lab because you cannot easily get enthalpy of formation of carbon. You cannot get enthalpy formation of oxygen because they don't have other elements to get them from. So for that case, we shall use Hess's law and other methods, right? So Hess's law states that if the reaction is carried out in a series of steps, if the reaction is carried out in a series of steps, Yeah, the enthalpy change for the overall reaction, the enthalpy change for the overall reaction equals the sum of enthalpy changes equals the sum of enthalpy changes equals the sum of enthalpy changes for the individual steps, for the individual steps at constant temperature and pressure, at constant temperature and pressure. The moment you know this thing in the head, then you can state. If the reaction is carried out in a series of steps, step 1, step 2, step 3, if it is carried out in a series of steps, the enthalpy change for the overall reaction from A to B, the enthalpy change for the overall reaction equals the sum of enthalpy changes for the individual steps at constant temperature and pressure. You can get your marks. Or someone can say at constant temperature and pressure, at constant temperature and pressure. Yeah, at constant temperature and pressure, what follows? The enthalpy change for the chemical reaction, the enthalpy change for the chemical reaction the enthalpy change for the chemical reaction is the same, irrespective of the number of steps or stages, irrespective of the number of steps or stages passed through, but will depend on the initial and final states of the reaction, on the initial and final or final steps, final states of the reaction. All these ones about the roots. One can as well say the enthalpy change for the chemical reaction is the same, whatever route is taken from reactant products at constant pressure and temperature. So whatever you were given, it is correct. Whatever you were given, it is correct. Whatever you were given is correct. Then it is after this that I can, I can talk about Laplace's law. Just I'll give you how it states, and we shall start from the Born-Haber cycle Z. Shall start from the Born-Haber cycle Z. So Laplace, I don't know how you read this name. It is the first law. Lavoisier. You can produce your child and you call her or him Lavoisier hyper, Lavoisier or Lavoisier, depending. Lavoisier Laplace. These are two people. You can call your child Laplace hyper, Lavoisier hyper. That child can be hot as far as chemistry is concerned. So with Laplace, I first show it using an equation. Carbon dioxide members under some heat, carbon dioxide gas can decompose or can dissociate to form carbon solid and oxygen gas. Let me say DH is equal to positive 393 kilojoules per mole. When is it dissociating? But combustion of carbon gives carbon dioxide, but since combustion is negative, it it means that our DH would be negative 393 kilojoules per mole, implying that on stating this law of Lavoisier-Laplace, it states that the amount of heat used to decompose a compound, the amount of heat used to decompose a compound, amount of heat used to decompose a compound into its elements, into its elements is equal in magnitude, Members, I'm sorry, but I was concluding. Let me state it. I say that the enthalpy basically, I said that the enthalpy of or the amount of heat used to decompose a compound into its elements is equal in magnitude, but opposite in sign to the heat given out when a compound is being formed. Because I wrote for you the equations, you saw how we formed a compound, you saw how we broke down the compound. So the heat involved when you're forming a compound, it is equal in magnitude, but opposite in sign when that compound is breaking. As simple as that. So I can't add on from here, just wishing you the best of the time and assuring you that this week is going to be one of its kind. I want to wish you the best of the day and urge those ones who have not made payments. We are many. This one may be, if it goes beyond today, from tomorrow I'll be entertaining those people who have made payments only. So I didn't want to, today is Easter Monday, I didn't want to put a show down, but tomorrow, make a payment. Let the last day be tomorrow. I wish you all the best. God should bless you until we meet again. Thank you guys for attending to the lesson.